Hi, Professor. My name is Chen Wang, and my teammate is Changpu Meng. We are from the Department of Computer Science. Our presentation topic is Security and Privacy Status Quo of Unmanned Underwater Vehicles. This is the structure of our presentation. Firstly, I'm going to talk about the introduction of security and privacy with unmanned underwater vehicles or UUVs. And some and secondly, I will talk about the previous works to see how things are improved with the development of network and hardware infrastructure. Thirdly, the feasibility, robustness, and security analysis of UUVs under different networking scenarios. In this section, we'll talk about the major roadblocks into the effectiveness as well as network security of UUV communication scams. What are the pros and cons of different networking strategies, and what are the regulations to the design and deploy of UUVs? Based on the analysis, we will move on to the fourth section, the security and privacy status quo. What's going on with the security issues right now? What are ways to solve the to be mentioned problems? What influence does it make to the future research topics? Then a brief discussion will talk about the comparison with different communication strategies and a couple of examples of how security and privacy matters are being taken into considerations while designing a qualified UUV. Furthermore, how UUVs can learn from flying drones as well as self-driving vehicles. Last but not least is the conclusion part. What is the current situation on the UUV networks? What can we expect from now on?
This is the introduction and the background information of our paper. Recall that in 1997, a world-famous movie was shown for the very first time. This is the story of a scam-rich herd adventure for the sunken Arctic crossing the cruise ship Titanic, as well as some love story behind it. In the movie, the UUV fleet is actually controlled by a human operator with a threaded cable stretching down to the deep ocean. The UUV in the movie was equipped with the hydraulic mechanic arms, sled drawing heads, cabled camera vision, and so on. Although by then this UUV must be a state-of-art technology, but even us can notice that the time delay between the human control and the machine execution. This is one of the flaws of with the cable threaded UUVs. To name a few: limited range, unreliable communication, electromagnetic interference, security and privacy concerns, and the lack of the effectiveness. Among all the mentioned limitations, one of the reasonable questions can be asked is, are there any of those flaws still exist in the design and deploy of the UUVs? The answer I'm afraid is still yes. But not all of them. Of course, our paper mainly focuses on the development of the security and privacy of UUVs today in order to provide a proper spec on what best described the status quo of the contemporary UUV technology. Suspectfully, this paper stressed heavily on the topic regarding communication protocols, routing strategies, optical operation algorithms, feasibility, and robustness analysis of the UUVs. All of this list topics contains a common issue, which is security and privacy. Security and privacy is the intrinsic characteristic of the different communication methods. It is safe to say that there are no intact communication, since intact only appears in an ideal world. However, this paper will explain the pros and cons of different communication methods in order to draw conclusions on future paths of creating a better protected communication way for underwater vehicles. Clearly, our paper is survey natured. Hopefully, it will extend the horizon to a more generalized unnamed vehicle technology, not only to UUVs, but also to UAVs, as well as the self-drive vehicles. Now let's move on to previous works. As of today, first thing to know above all, there are two types of UUV that are taken into consideration in this paper. The first kind is called remote operator underwater vehicles, or to simplify, ROUVs. Typically speaking, ROUV is three-third underwater mobile device. One example is underwater drawing in the movie Titanic. This kind of UUV is frequently used for geographical and oceanographical exploring purposes due to its stationary requirement. The ROUV communication architecture is shown in the figure here. A DC power supply is connected at the water surface. The cable plugged into the ROUV through a physical cable. A chipboard converter within an electrical cage is applied for regulating the output voltage for different electrical and electronic devices. This goes without saying that with the cable presenting, ROUVs must comply with the standards such as the military standards 461. But beyond this, the system has already taken security and privacy into consideration. In most cases, ROUVs are offline since the remote operation holds the overall control authority. In this case, the information protection is self-contained, except for physical typing and bugging. There are no better means to protecting the cable layout. The second kind is called autonomous underwater vehicles, or RUVs. One notation here is that in the paper and this presentation, we will use UUV as the named, but essentially AUVs are equivalent to UUVs for the sake of names. Unlike ROUVs, an AUV is a robot that travels underwater independently from direct human operation. It has the path-finding ability and geographically navigation skills that enables itself for a variety of applications. So far, the most recent literature are concerning RUVs as their equipment under test. Several recent studies shown that AUVs have excellent path-finding abilities with the fast marching-based approach, or FM approach. A model result is shown in the figure that a well-developed FM method in executing give tasks under a demanding underwater environment. From the figure, breadth the first search, or BF search, gives the supreme authority to pattern founding configuration, but with relative, excuse me, relatively higher resolution and heavier computation bound for the gradient descent. While for FM it gives almost the same path at the same math degree comparing to BF with more friendliness with resolution and communication. Nowadays, a growing body of literature showing the various communication strategies among UUVs and surface stations. The most commonly used networking method is ad hoc network. Ad hoc network is a type of temporary computer-to-computer connection. In ad hoc, a wireless connection can be set up directly to another computer without connecting to Wi-Fi. This connection makes it possible to long-range routing such that its power permits the traveling distance will no longer be a concern, with which is considered to be a popular choice among all the options. With the chosen optimal routing algorithms, UUVs have been used for heavy underwater construction works, especially within the dangerous waters. This job assignment is similar to the vehicle routing problem, but with the length of the difficulties in it. The optimal routing algorithms performs as a supervisor to assign text to its UUVs as well as monitoring the work progress. The goal of the vehicle routing programs is minimize route costs. That's why the job assignment for UUVs are super sensitive with degrees and levels. This table shows different type of connections types with their pros and cons. Two type of the communication schemes are listed. The first one is centralized, and second one is decentralized. For connection architectures here both have the advantage and the disadvantages, but obviously the multi-layer and hoc network is favorite of all. In this way, the computation and communication loads will significantly reduce, which also facilitates a more secure and reliable networking system. Here are the list of 4 communication candidates, and multi-layer and ad hoc network works best. For features make the standard out are interchangeable network connectors, supervising power described to the UUVs, computation and communication loads reduced, and a more secure and reliable network. As for the multi-hop routing, it typically works in radio network as such that it have a wider coverage area. In one of the reform paper, the authors applied the dynamic data driven application system with the multi-hop for UUVs to discover static targets in such space. From the expansion, the signal power receiving PR in reversely proportional to the distance d. Pt is transmitting signal power for more than 2 nodes within such space. The challenge here is finding the best multiple hop configuration for UUVs. This can be achieved by using Dix algorithms. The adopted algorithms in the paper, but the comparisons of the system performance between ordinary connection and multi-host connection is shown in the table. There are two indices used here: target found ratio and collision avoid ratio. From the result, the multi-hop communications successfully prevents collisions between U-joints with the storm in the organized band. However, this method is only able to detect the strange target, which have the luckiest limited the usage of this system. UUVs are important in areas that is isolated from the surface and require complex tech states. So the comparison between the multiple UUVs is also important. The UUV ad hoc networks, a well-established communication scheme is proposed, which is called three-tier communication scheme. First, UUVs are divided into two categories: master joins and slave agents. Master join directly connected to the mainstream communication with the surface. This communication is Tier 1. The surface control passes along the orders directly to its master joins. In the meantime, the master are also updating the work situation and conditioners back to the surface, which make Tier 1 a two-way traffic channel. Also, master joins are equipped with the basic AI enable them to describe works among all slave agents or just the agents. The description of the works consists of the working area, workload, working distance, work type, and so on. The communication between master and agents are Tier 2. Subscribe the connections. Tier 2 is passed down communication channel such that the agents cannot initiate the conversations with the masters. Under this Christmas system, this can be understood that all agents joins the given tests of certain subject, as known as works, the under specific period of time. They are expected to complete the task. Masters are supposed to examine the working environment and evaluating level to different difficulties in order to give a reasonable description of work and assign time. As for the swarm and agents, communications between the peer agents, namely the Tier 3, the interconnection are encouraged in order to exchange the core environmental information such as lighting condition, fish school text, unexpected for performance error, and so on. Since there are no upstream of Tier 2, it's important for master to receive feedbacks of agents unless the retrieval. The communication scheme between agents and with hits in the local area network. No broadcasting is needed since this purely offline amongst peers. At this point, you may ask, if one or more agents are affecting critical maintenance issues during the work, how would them let the master know of it? This can be considered as a classical coverage problem. A proper way to solve it is applied to the SP criterion. And AN represents the number of the workloads per agent ratio. This value is quantifiable based on the assignment of the master join. BN is the work complement ratio. So the ratio between A and B is the percentage of the interim job and described to the every single agent drawings. In addition, the difference between two agents represents the difference in progress of completing the assigned jobs. This idea is an adoption of the optimized linked state routing method. In a case of an agent malfunction, this difference becomes noticeable large at the point of the retrieval. The unfinished job can be re-evaluated and re-signed, while the malfunction agent will be temporarily and decommunication and sent to the maintenance. As for the agent, once the performance is compromised, it will automatically run self-checkup and evaluate damage. Then the service adequate energy for the self-retrieval and applies to the rest of the assigned job. If the damage impacts the mobility, that self-retrieval is not achievable. The interconnection amongst other agents will put into effect, and the agents can put together a rescue mission, no one left behind. The conclusion of section 2. Let's move on to the next section.
The feasibility, robustness, and security analysis under different networking scenarios. Let's first take a look at the networking influence on location. As for the rapid development of UUV for commercial uses, the control of them also becomes an important aspect for safety concerns. Not only the UUVs will affect the radar images near military sites and other location-sensitive areas, the communication system of the UUV might also cause radiated emissions to other communication channels. The radiated frequency range regulations are shown in the table 3. 30 MHz is roughly the threshold for emissions, from chopped with conductors to emissions to the air. Since the V in UUV stands for vehicle, in this paper, it is considered that UUV is complying with the automotive vehicle related EMI regulations. So, ad hoc network is dynamic network, which can be formed anywhere with just 2 basic nodes. It doesn't require any centralized infrastructure. The main issue for the security connection is to set up a closed-loop network so that the effects from outsiders can be minimized. The UUVs commonly utilize ad hoc networks. If without any shielding techniques, the UUVs are strictly banned near certain locations like military facilities, shipdock, and other location-sensitive areas. The ad hoc communication interference can be described as in the figure. Typically, the connections are set up among ground and surface station. However, the illegal flying UUV is also able to send signal under the same networking protocols. This unexpected signal might cause the normal communication failure or even serious accidents. The second aspect is depth and speed in terms of communication efficiency. According to several referred papers, the two most important attributes in judging communication efficiency are equivalent isotropic radiated power and navigating attitude index. With that being said, the integration of ad hoc and multi-hop networks sums up the advantages of both, also removes parts of the limitations. To start with, the multi-hop network provides security in connection such that the UUV itself will not be interfered by outside signals. In the meanwhile, agents also have the ability to group chat with other agents. It further enhances the data protection and limited radiated emission. Secondly, the ad hoc network is well known for multi-point direct connection, such that the importance of surface station has been weakened. This leads to a wider routing distance and longer flying range. In addition, agents in ad hoc networks consider targets in a single mission as a teamwork. Hence, in this integration, it plays a better role than multi-hop run by itself. Let's take a look at an example. A commercial UUV type named Romas 100 is listed in the table. It's powered by internal batteries. The maximum navigation range is 72 kilometers, and the frequency of transponder is ranged from 20 to 30 kHz. The emergency transponder is equipped with mission alert and emission tracking capabilities. Also notice that the normalized communication frequency is rated at 300 kHz. The spectral analysis under different power density is shown in the next figure. For this figure, we know that further away the UUV are navigating, the scatterer the power density would be. Okay, so the third aspect here is navigating range constraints under networking protocols. A basic relationship between distance and signal intensity is followed by the inverse square law. In other words, the distance is always inverse square proportional to communication efficiency. From the field test, the navigating range is represented by the number and density of nodes that spread underwater via ad hoc networks. The contribution of nodes follows normal distribution, which centralized around the target. Higher node density results in a more reliable and frequent network communication. But if the routing algorithm was not well developed, there is also a growing chance for collisions. This relationship can be shown in the figure here. The horizontal bar is the normalized distance d. When d equals 0, the distance between sender and receiver is 0. And when d is at negative 1.5 or positive 1.5, the distance are both at maximum. In this way, when signal intensity is at its maximum, and the communication efficiency is about 94%. Okay, so now the fun part: security and privacy status quo. In most applications, underwater communications can be accomplished by radio, optical, and acoustic waves. To have the correct choice of communication medium, a brief discussion regarding the different ways of wireless communication and possible challenges in underwater situations are shown in the table. From the table, optical waves have the highest data rate, while acoustic waves are able to transmit deeper in the ocean. So it is our job to distinguish which is the most safest way to communicate. What network security features we need to focus on. Before expanding the UUV technologies into vast commercial and military applications, improving data transmission security is the most important problem we need to solve. As at the 2017 RSA conference, the Verizon risk team presented an interesting case. A group of Somali pirates hijacked a cargo ship. This group of pirates did not target people, but specific goods, and eventually robbed valuables. So the pirates were able to escape quickly. During the investigation, the risk team noticed that the company's transportation management system had been destroyed before the actual attack, which means that the pirates were fully prepared for the robbery and they already know their target. This is why having an advanced network management system is so important. With this system implemented, the network itself can monitor the status of the cargo as well as the ship in the meantime. However, the better truth is that this system is still with high implementation costs and even higher maintenance costs. That's why most of the companies are still in the freewheeling status. The freewheeling refers to the lack of proper protections in regard to data leakage. So in this case, let's first introduce a stable and reliable UUV power equipment. From this figure, is typically electronic machine drive system with an intelligent invert and joint drive propulsion system. Besides of double power supply, the electric propulsion is also more stable, and it is easier to achieve a remote control scheme. However, in the current context of accessible labor costs, ship owners are clearly more inclined to hire crew members to operate than the additional costs of adding a propulsion system or using electric propulsions. So we've already solved the problem number one, which is the stabilized power supply. Now let's move on to problem number two. For commercial use, three major modifications to enhance the data protection are to be made with lower cost on the energies. With that, the reliability is increased and system complexity is tested to be sustainable for most attacks. Firstly, using an anonymous signature at the wireless mesh network. The advantages of WMN include minimizing the dependency on the internet. This solves the problem of having signals misguided via transmission. Secondly, multi-hop networks were implemented in order to prevent eavesdropping without knowing the attacker's address or channel station information. This method is mainly targeting the physical layer security of multi-hop networks, where an end-to-end secure connection probability was defined to and used in a refined Bellman-Ford algorithm. Thirdly, pretty good privacy combined with gate constitutes a multi-level integration for enhanced network security. This method has a decentralized nature, which is solved safety issues in Gate itself. Gate with PGP ensures the integrity via signatures by confirming that its content is exactly the same as the content on the workstation of the developer who created the label, and the submission of the signature is almost impossible to counterfeit without accessing the developer's PGP. In this figure, it compares the performance of the greedy algorithm proposed by the author with the traditional shortest path algorithm and further evaluates the predicted position information of the proposed algorithm at different average node speed. The results show the success probability of transmission decreases in turn. When the network is more dynamic, more nodes will leave the communication range of their neighbors so that the probability of success will decrease. The reliability of remote control is also a key technical problem that UUVs need to solve in the future. Compared with airplanes, trains, and cars that have already achieved one-person driving, ships are currently recognized as the most difficult transportation for human control. In the picture here, the multi-purpose offshore vessel Luna is able to run through the waves in harsh sea condition. The ship the size of this ship is small and flexible and is equipped with a high power propulsion system. As we mentioned before. For UUVs, various types of signal and control system ought to be used to replace turbine managers to monitor and control the operating conditions of equipment on board. Compared to ships, the underwater environment is relatively mild without the influence of waves and winds. Thus, factory rates of mechanical and electrical failures for UUVs can be reduced by designing a more robust control panel, improving water isolation and heat ventilation abilities. A side effect of having an unmanned vehicle is to prevent the vehicle from human error. However, without a comprehensive design feature, it also bring in more unexpected, unintentional risks. The technique, the technology development on system security and reliability should be done at the same time concerning laws and regulations. In this regard, it seems to have a long way before the integrity in the development of safe, reliable underwater vehicles.
Okay, next, let's jump to the discussion section. So all we did here in this paper is trying to find the best secure communication channel for UUV networks. We have dicta allograms, we have distance-based joint network-ready routing allograms. Both of them have shown a considerable improvement over the traditional communication allograms with the highest efficiency and better protection skills. However, disadvantages also can be ignored, such like huge time delay, demand bounded, no cost effective, and so on. So in order to safety higher demand of network security in UUV commander and operation, researchers are now more likely to promote solution based on the technical report NORAD. The marine used UUVs have a secure network infrastructure called Marine Domain Awareness, or MDA. MDA is defined by the International Maritime Organization as the effective understanding of anything associated with the maritime domain that could impact the security, safety, economy, or environment. In this special case, Navi UUVs has installed advanced quality of service traffic authority as well as protection timing protocol to enable time stamping with the nanosecond accuracy. Furthermore, to protect the onboard mission data, the platform developer required an operation operating system with chipboard network attacked storage serving for the UUV embedded computers. In addition, a system architecture is small from mission process called commercial off the shelf, which is COTS. Combined with NAS, the ensure the UUVs is under multiply layers of protection for the network security, while demand stable data transformation in a timely manner. As of today, more and more IT companies are working on self-driving technology such as Mercedes, BMW, Google, Pony AI. Pattern recognition also becomes an undivided segment in the realization and security. At this point, one question researchers is that what can we learn from this? Underwater environment is somehow similar like the on-road traffic environment. A pattern recognition also can be useful for UUVs in avoiding potential security issues. A public demonstration of the pattern recognition provided by Pony AI is shown in the figure here. The entry system is under local connection in order to prevent malicious system branch from outside. The isolation of the system has the advantage of system attacking by the inconvenience for information blending and interconnection.
Finally, the conclusion part. In our paper, we first introduced the feasible communication methods and applications, and then showed the pros and cons of different network strategies and communication efficiencies. Based on all that, we explained in the length of potential network security features on UUV, both power supply topology and network security setups. We know that stable and reliable power drive is the key. Then multi-layer protection of network communication is also important. Several proposed security implementations are have advantages, but also with some disadvantages. In this case, more reliable UUV networks with advanced communication and protection features are still needed for the research efforts. This concludes our paper and this presentation. Thanks for your attention, and our team members are Chen Wang and Changpu Meng. Have a nice day.